Okay, should you go for the awesome donut or the Cheerio? Obviously, you go for the grand bacon donut because bacon, right? Nobody goes for the Cheerio. But actually, if your gamma value is 0.99, do you see that going up for the big donut is, if this is 0.99 right here, and then this is 0.99 squared, and this is 0.99 to the third, and this is 0.99 to the fourth power, that's still a lot better than 2, right? 0.99 to the fourth power is 0.96. So with 96% pull, you're going for the awesome donut, and with 2 times 0.99, which is 1.9 something, you're going for the Cheerio. And we all agree that's the right decision, is go for the awesome donut, right? Because it's far away. If your gamma is 0.01, what are you going to do? Well, 2 times 0.01 is 0.02. So there's 0.02 pull going for the Cheerio. And 100 times 0.02 to the fourth power is ridiculously small. So if gamma is very small, that Cheerio is starting to look better than the awesome donut, right? Why? Because this agent values near-term rewards more than long-term rewards. So this is back to the children with the marshmallow experiment, Harvard experiment. Basically, this is a child who cares about the marshmallow right now. And if gamma is 0.99, that's a child who cares about the long-term benefit. What you're doing when you adjust gamma is you're saying, how far into the future do I really consider? If gamma is exactly 1, what does that do? That says a reward tomorrow is just as good as a reward today. Would you rather have a donut today or a donut in 6 years? I can't tell the difference. They're both equally good to me, right? That's almost getting irrational because it feels like there should be a little bit of a discount, right? Okay, what happens if gamma is greater than 1?
You never want anything.
Yeah, it's like, yeah, I could have a donut today, but oh, I'd so much rather have one in 3 years. That just seems kind of irrational to me. Maybe there's a reason where that makes sense, but anyway, sorry for giving a super long answer to a simple question, but if I just gave the answer, I think it wouldn't make as much sense as if I explained the whole thing. So really it comes down to what gamma does. What if gamma is equal to 0? It does not care about the future, it becomes greedy. It makes whatever action will give it reward right now. So it'll go for the Cheerio for sure. Looking at that awesome donut has no value to it because 4 steps away, that's just too long, worthless. Okay, so you get what gamma is, but adjusting gamma also affects what the accumulated rewards will accumulate to. So one possible thing you could do, here's a really simple solution. Suppose you wanted to guarantee that no matter what, the maximum Q value, which would be this thing, 1 over 1 minus gamma, would converge to 1. How could you ensure that happens? Math, yeah. You could store in your Q table. Whenever you update your Q table, update it with whatever you've got divided by that equation, which would calculate the 33.33 in this case, and so then it would converge to 1. Then you would be totally free to tune gamma to your heart's content, the discount factor. You could tune the discount factor to anything you wanted, and the maximum possible Q value in your table, which is the one you get if you get the maximum possible reward at every single time step, would max out at exactly 1 because you're dividing by that amount. So you could make this thing a little bit more robust to allowing you to tune the parameters without having to mess with it. In my opinion, that should be built into the algorithm. And I could do that. I could come here to the pseudocode and say divide by 1 over 1 minus gamma when you put it in the Q table. Would that affect the decisions it makes in any way? It would not, and here's why. Look how we make decisions. For every action, we check the Q value and we pick the biggest one. So if we divide the Q values by 1,000, the biggest one is still the biggest one, right? If we divide by 1,000,000, it may be 1,000,000 times smaller, but it's still bigger than the other one scaled down by 1,000,000 too. So Scaling it makes no difference. So yeah, I think it should be built into the algorithm. But if I do that, if I just say, oh, where would we do that? I guess it'd be in this equation. I'd add to this equation, divide by 1 over 1 minus gamma, which would actually be the same as multiplying by 1 minus gamma. Then you would forever think that was part of the Q-learning algorithm, and then you go read other papers on Q-learning and you'd say, where's that term that Dr. Gashler taught me? It's missing. I think you kind of have to understand it so you can work with other people's implementations of Q-learning. So that's why I didn't teach that, but there you go, now you understand it. That came up. Let's look at my vec.java. Normalize. What is normalization? So I understand that a lot of you aren't going to look very deeply at my code, and I get that, but I do want you to understand these operations. What does normalizing a vector do? Basically, it makes sure that the magnitude of the vector comes out to be 1. Here's how it works. I compute the squared magnitude, and then I divide by the square root of the squared magnitude. Why didn't I just compute the magnitude instead of the squared magnitude? Turns out this is slightly mathematically faster. Well, sometimes you want the squared magnitude, and square root is a slow operation, so that's why it's written in that funny way. But basically, all I'm doing here is I run through every element in the vector, and I multiply by 1 over the square root of the squared magnitude. In other words, I'm dividing every element by the squared magnitude. What this does is it makes the vector have a magnitude of size 1. That's called normalization. Specifically, I'm normalizing the vector to have a magnitude of size 1. I do want to emphasize that's not the same thing as normalize. Right here I say, neural networks learn best when the input target values fall approximately between -1 and 1, so I recommend normalizing the values to fall approximately in that range. So because that word normalizing occurred, and because I have normalize right here, a lot of students said, oh, we should call this method, and that's cool, but this is a different type of normalization. Well, this normalizes the magnitude of the vector, and this is normalizing the values to fall between -1 and 1. Do you see the difference? One is, so first of all, the target values are not, oh, they are a vector. I can see why this is very confusing, and I apologize for the name clash. But what I mean here is I want all the values in this target that happen over time. I want the smallest one you ever see to be -1 and the largest one you ever see to be 1. Now, notice that's not the same as the reward, right? The reward is a component in this equation, but what I'm saying is the Q value that you see. So what it really says here, this normalize thing, is divide by that 33.333, divide by 1 over 1 minus gamma, or divide by something such that those values don't get too big. So if you were doing this empirically, you would just print maybe to the screen what your Q values are that you're putting in your neural network, and you'd say to yourself, oh look, the biggest they ever get is about 33, the smallest they ever get is about 0, so we'll just divide by maybe 40. And that'll cram them all in the range of 0 to 1. And that's what I meant by normalize. In this case, don't call my normalize method if you do. If you just take a vector of size 1 and you normalize it, what's going to happen? It's going to become the number 1, because that will be a vector of magnitude 1. Okay. Sorry, I talked about that for a long time because that came up, but I think I missed your question. That was it? Okay, great. Cool. Are these things helping you understand the Q-learning algorithm? Sort of. Okay, well that's better than not at all. So we're making progress. All right, let me show you something else with Q-learning. Demos, car on hill, bin. Here's a classic problem that is done with Q-learning. I'm going to switch it to mouse mode now. This is a car. The car is on the hill. I programmed it to chase my mouse. So if I move my mouse to the left, the car goes into reverse and it tries to get my mouse. If I move the mouse to the right, it goes to the right. The problem is this hill is really steep and the car's engine is really wimpy. So the only way to get over that hill is to kind of rock back and forth, and then it gets over the hill. Does that make sense? Rock to the left, rock to the right, rock to the left, rock to the right. But even though it has a wimpy engine, if you do the rocking thing, there's more than enough power to get over that hill. See that? Okay. So there's my game. Now I'm going to switch to a Q learner, and you can see what's happening right now is, see that little arrow at the top that says which way the gear of the car is. So it's trying to go forward, it's trying to go back, and it's not really achieving the goal. Why? Because it's stupid. But if we let it train for a darn long time, it will eventually learn what's going on and get over that hill. Now, how long would you imagine this would take? It also depends on how we reward it. It depends